Hi everyone, today I present a joint work with Aurélien Greuet, Guénaël Renault and I, Simon Montoya, about our paper named Attack on LAC Key Exchange Protocol in a Key Misuse Situation. So first, I introduce the context of our paper. In 2016, NIST called for post-quantum safe cryptography, mainly for signature and key exchange mechanism. Today I present LAC, which is a lattice-based key exchange mechanism, and this scheme offers three security levels. The NIST asked for theoretical and practical attacks on this candidate, and today it's a practical one in a misuse context. So we attack a key exchange protocol of LAC. So what is in general a key exchange? Suppose that Alice and Bob want to agree about a common session key. So first Alice generates a key pair. She sends to Bob her public key, and with this public key Bob encrypts a message R to obtain a ciphertext C. By hashing Alice's public key on R, he obtains his session key. Then he sends to Alice his ciphertext. To obtain R, Alice decrypts C with her secret key, and to obtain the same session key, she hashes her public key with the plaintext R. So just like it's a NIST candidate until the round 2, and it's a finalist of the Chinese competition for post-quantum crypto. LAC teams propose two key exchange protocols, a classical one and an authenticated one, which is roughly a key exchange plus some verification on the ciphertext. What is the normal context of key exchange and authenticated key exchange? For the key exchange, Alice does not keep the same private key for several key exchanges, but any verification is done on the ciphertext. For the authenticated key exchange, Alice keeps for several key exchanges a static private key, but some verification is done on the ciphertext to ensure that it's not a forged one. So now what is our misuse context? Is when Alice keeps a static private key for several key exchanges and any verification is done on the ciphertext. So why we want to study this misuse context? So first, a server can implement a key exchange with a static private key without verification to gain internal performance. So we need to assess the security impact of this implementation, but it's a wrong implementation. And the most important motivation is in constrained devices. A fault injection can bypass the verification done in the authenticated key exchange. So if the verification is bypassed, we are in the case of Alice keeps a static private key for several key exchanges, and any verification is done on the ciphertext. So for these two reasons, we need to determine the resilience of LAC to this kind of attack. Here I give a summary of our paper. So we attack LAC key exchange protocol in a misuse context. We attack the three security levels. For the first two, we need at most two key exchanges to retrieve the entire secret key. For the third security level, we need at most 8 key exchange per coefficients. And our attack is implemented on a LAC reference code. Here I give some assessments of our attack. So timing results have been evaluated on my laptop. So in average, we need at most, here the average is the key exchanges required to retrieve the entire secret key, and here is the timing to retrieve the entire secret key. So now I will give some notation for the following. So let Q equal to 251 and we define ZQ, which is Z over QZ. We define a polynomial ring RQ, which is ZQ over x to the n plus 1, where n is equal to these two values depending of LAC security level. For a given polynomial in RQ, we can represent the polynomial as a polynomial or as a vector. And to speak about one coefficient of the polynomial, we can use these two notations. I need to introduce error correction code. So an error correction code can correct information which can be altered during a transmission. So suppose the sender wants to send a code word 101 to a noisy channel. The receiver receives a code word 001, which is different from the original message, but by using a decoding algorithm, it can retrieve the original message, which is 101. This kind of code can correct only a fixed number of errors. In LAC algorithms, they use a BCH error correction code. To encode a message M, the encoding algorithm is to pads M with some redundancy to obtain a code word CW. And this binary BCH code can correct at most 16 errors. So now I will present briefly LAC algorithms. So LAC is based on the hard problem ring learning with error. So let B equal to A times S plus E, where A, S, and E are random polynomial RQ. With the knowledge of B and A, it's hard to retrieve S. Now I will introduce the key generation. So first we generate a random polynomial A in RQ. Then we generate two random polynomials in RQ with coefficient in -1, 0, 1. We compute B as previously, equal to A times S plus E. And then the public key is A and B, and the private key is S. So with the knowledge of the public key, it's difficult to retrieve the secret key. Now I will give some idea of the encryption and decryption procedure. So suppose that we want to encrypt a message M. First, we construct C2 as our message plus some noise, with noise depending of the public key. C1 is information about the noise in C2, but is only useful with the secret key. The idea of decryption is to use the secret key with C1 to delete the noise in C2 by computing C2 minus C1S to obtain M without noise. But it's not exactly that. When we compute C2 minus C1S, we obtain M plus small noise. So to differentiate a 1 coefficient to a 0 coefficient in M, we need to multiply it in C2 by Q over 2. So what we obtain Q over 2 times M plus small noise. So if the coefficient was a 1, then it's Q over 2 plus small noise. So we are in the orange part. And if the coefficient was a 0, then M plus some noise is just small noise, so it's close to 0, so it's in the blue part. LAC algorithm uses an error correction code to remove the small noise, to remove more noise. So what is the encryption process for a message M? First, we encode the message to the BCH code. So we obtain CW. After that, we generate 3 random polynomials, R, E1, and E2 with small coefficient, -1, 0, 1. Then we compute C1, which is RR plus E1, is the information vector of the noise in C2. And C2 is B times R plus E2 plus Q over 2 times CW. And then is our code word plus noise. And then we have our ciphertext, which is C1 pads with C2. For the decryption algorithm, so first we compute M hat, which is C2 minus C1s. As previously, is to reduce the noise in C2 and to obtain Q over CW plus small noise. The step 2 is the reconciliation step. So it's to compare the coefficient with the blue part and the orange part as previously. So it's Q over 4 and 3Q over 4. If the coefficient is between this coefficient, then the code word coefficient is 1. Otherwise, it's 0. And the step 3 is the BCH decoding to obtain the plain text. So now I will talk about the attack on LAC key exchange protocol. So our context is Alice keeps a static private key for several key exchanges. We will act as Bob, so we will forge ciphertext C without encrypt a random message R. Here we want to retrieve Alice's secret key, so we need to decryption algorithm, because it's only here where the secret key is used. So now we suppose that Alice keeps her private key for several key exchanges. So and more precisely, S is used at the first computation of M hat. I talk about this attack in 3 steps. The first step is to control the decryption procedure of Alice. So we send a forged ciphertext, and we want to determine what Alice will obtain after decryption without any knowledge of the secret key. So to do so, just a reminder, each coefficient of the secret key belongs to -101. So suppose we forged C1 as A, with A lower than Q over 4, and C2 coefficient is only Q over 2 or 0. And we send this ciphertext to Alice. What Alice will obtain after decryption. So this step 1 is the computation of M hat. So Alice will obtain coefficient equal to Q over 2 minus A times a coefficient of the secret key, or just minus A times a coefficient of the secret key. This step 2 is the comparison with Q over 4 and 3Q over 4. So what Alice will obtain? If the coefficient is Q over 2 minus A times the coefficient, the value is always between Q over 4 and 3Q over 4, because A is lower than Q over 4 and the secret key coefficient is equal to -1, 0, or 1. The coefficient with only -A times the secret key coefficients are always lower than Q over 4 or greater than 3Q over 4 by a modular reduction. So after comparison, the code word coefficient is always a 0. So what Alice have? She has a code word with 1 when C2 coefficient is equal to Q over 2, and CW coefficient is equal to 0 if the C2 coefficient was equal to 0. And then Alice obtained M by decoding the code word. So with this method, we can send a forged ciphertext and determine what plain text Alice will obtain. More generally, we can forge C1 as -A times a monomial, with A lower than Q over 4, and C2 coefficient equal to Q over 2 or 0. But with this forged ciphertext, we don't learn any information about the secret key. So now we need a construction which allow a key guessing. So we foresee one as previously, but with one restriction, that which is greater than q over 8, and as previously lower as q over 4. And C2 is equal to the first coefficient our key guess, 8 times our key guess S prime k, and after that every coefficient is equal to 0 or 1, q over 2, sorry. So this step 1 of Alice, so we send this ciphertext, and what is this step 1? Step 1 is the computation of M hat. So what Alice will obtain, except for the first coefficient, is as previously, so minus a times secret key coefficients, or q over 2 minus a times a secret key coefficients. So here we will look only at the first coordinate, because the other are as previously. So this step 2 is comparison with q over 4 and 3q over 4. If our key guess is equal to the opposite of the secret key coefficient, then Alice obtains a times plus or minus 2a. So our a is greater than q over 8 and lower than q over 4. So plus or minus 2a is always between q over 4 and 3q over 4 in RQ. So Alice obtains a 1 at the first coordinate. If we do the wrong key guess, a times s prime k minus sk is equal to plus or minus a or 0, which always give a 0. So Alice obtains a code word with a 1 at the first coefficient only if we did the good key guess, and otherwise she obtains a code word with a 0 at the first coordinate. So if we have a distinguisher to distinguish when Alice obtains a code word with a 1 or a 0 at the first coordinate, we can send first a forged ciphertext with s prime k equal to 1. If the distinguisher ensures that Alice obtains a code word with a 0 at the first coefficient, then we learn that the secret key coefficient is not minus 1. If it was a 1, then the secret key coefficient is a minus 1. So if it is not minus 1, we send a new forged ciphertext with our key guess equal to minus 1. As previously, if Alice obtains a code word with a 0 at the first coordinate, then we know that the secret key coefficient is not 1. And if it's not minus 1 and 1, then the secret key coefficient is 0. So now we need the distinguisher to distinguish when the code word has a 0 at its first coordinate or 1. So how to do that? The issue is most of the time, so Alice obtains the plain text by decoding this code word, and most of the time the BCH decoding of a code word which differs of only one coefficient will give the same plain text. So now we need to play with the boundary of 16 errors. So LAC BCH code can correct at most 16 errors, and a decoding failure occurs when the code word has 17 errors. So how we can use that to learn information about the secret key? So first we forge C1 as previously, so minus a times a monomial, that ensure during the computation of C1s that the coefficient k is at the first coordinate. Then we construct a code word with a 1 at the first coordinate. It's easy to do because the encoding algorithm is the message m pads with some redundancy. So we only need to put a message m with a 1 at the first coordinate. Then we inject 16 errors to the code word except at the first coordinate. Then we construct situ such that Alice, after comparison, she obtains this code word with 16 errors, except for the first coefficient. It will be our key guess. So to do so is when the code word coefficient is a 1, so we put a q over 2 in situ. Otherwise we put a 0. And at the first coordinate we put 8 times our key guess. So what Alice obtained with this false ciphertext after decryption. So after step 1 and step 2, Alice obtained C1 with the first coefficient equal to 1 if we did the good key guess. Otherwise, she obtains a code word with a 0 at the first coefficient. So why? Because as previously we show that if C2 coefficient is q over 2, then the code word coefficient is 1. So here, except the first coordinate is exactly the code word with 16 errors, and the first coordinate depend on our key guess. So here we have a distinguisher. So if the code word has 16 errors, then the BCH decode will decode the BCH decoding algorithm will decode CW1. Otherwise, a decoding failure will occur. So the distinguisher is if we have the same secret decision key as Alice, then we did the good key guess. Otherwise, we did the wrong key guess. So what is the attack? First, we send to Alice a false ciphertext with our key guess equal to 1. If our session keys match, then the secret key coefficient is equal to -1. Otherwise, we send a new ciphertext with a key guess equal to -1. If our session keys match, then the secret key coefficient of Alice is equal to 1. And if it's not -1, is not 1, so it's 0. So we see that we need at most 2 key exchange to determine one coefficient of the Alice's secret key. To conclude, here we have shown this attack apply for the first 2 levels of security, and we have shown that we need at most 2 key exchange per coefficients. In our paper, we have an adaptation for the third security level, which have an additional encoding, and we show that it's an attack on a LAC key exchange in a misuse context. It's the end of the presentation. Thanks for listening. Bye.